Hi, welcome back to Book Club. We're actually finishing up today the aircraft design book. Again, this is a phenomenal book. Go read it at the point of book club. So I'm here to hit the wave tops and explain some of the key concepts and guide you through it. But ultimately, dear reader, it's on you to kind of dig in, really crank on the homework. You can really self-teach yourself a ton of things, including aircraft engine design. This is a great starter book for those who are interested in getting into the field. And so this last one, really this book is designed from sort of this handoff from the vehicle design level and then sort of systems engineering design all the way down. And last chapter, we've kind of been down to the components. So we talked about the combustor, and this time we're talking all about inlets and nozzles, sort of the air coming in, the air going out. And so this will wrap it up for this book club. And so what we want to talk about is the recovery, so inlet recovery. And ultimately, there's a sort of pi, right, the ratio of pressures, inlet recovery. And there's the total pressure at the inlet divided by the pressure of ambient. Now, the total recovery here is related to the Mach number. So this is gamma minus 1 over 2 Mach squared, and raised to the gamma over gamma minus 1. Remember, the gamma is just a ratio of specific heats. Mach number squared in there. I actually showed in Kuchaman, I think it was the Kuchaman lectures, maybe the sort of the fluid mechanics lectures, why this actually shows up. And when, it does start stacking up. Not so much in the subsonic world. You do have a little bit of help as you're going faster and faster subsonically, but it's really upon the supersonic for sure, where you get a lot of help. Okay. Now inlet design has a lot to do really the four major things. I'll change colors here. So the four major things for an inlet. One is sound. Right, the sound regulations, kind of airports are always getting stricter and stricter. You can absolutely hear it. I mean, you can hear like this really kind of cranky. You listen to an airplane take off, you can hear it. Where I live in Houston, is sort of under the during some directions of takeoff, I can hear the sort of the south-left planes coming out of Houston Hobby, and it's like I can absolutely hear that. Just like any aircraft flying overhead, you hear it at a lower altitude. So sound is a big one, as regulations are getting more strict. And then blade out is actually the other one. So really, and I've talked about this before, the reason the engine is encased is mostly because of this blade out. It is some of sort of helping the air diffuse, but a jet engine is ultimately this core engine that's driving a fan. So it really is closer to propeller driven than anything else. But that casing does have some to do with airflow, but it's also quite a bit to do with the blade out. In fact, you want some pretty cool videos, go search that blade out on YouTube. You can see the test where they basically explosively release a blade and just some of those, as I said before, the jet engine is a very amazing design that we humans have done, and sort of watching these like explosive tests are pretty crazy. It's super important to do, but it's always that humbling. Wow, you scrapped a really good piece of hardware for that test. It's always amazing. Okay. The other one is engine out. We talked a little bit on that from the combustor sound side, but this is actually called then windmilling. And you have to be able to handle some speeds. Now you can absolutely say, hey, if aircraft, your engine goes out, you really need you to get down to the speed and altitude, but you have to be able to handle an engine out at any altitude and not be destructive. And so that's that windmilling side of things. I've talked to a couple SR-71 pilots, and we can happen with the air inlets. You can get basically the boundary layers grow, and you can actually have the supersonic compression sort of kind of come out the front. It's called an unstart, and so that engine, it would be pretty violent. The pilots would talk about you would sort of hear it coming, and they only have like a second to really, because you had twin engines at SR-71. If one engine went out, you'd have that immediate yaw. That's actually why the vertical stabilizers or inward pointing actually helps on that yaw, but they'd have to catch that pretty quick, or otherwise being in a flat spin, just the size of the engines and the drag that they create when they're off. Okay, so that was a big one. And then inlet distortion. So this is really the jet engine compressors and the fans, because there's a fan compression ratio. They don't handle a ton of inlet distortion. What do we mean by this? So if you're looking directly onto the aircraft, it's sort of here's the nose, and then here's sort of the outer blades. The inlet distortion would be, let's say if I was looking, contours of pressure, if there were some sort of lower pressure zones down here at the bottom for whatever reason, then the blades would be fully loaded up top, but only partially loaded. In fact, they'd have a moment on them. You'd actually bend them a little bit. So it's can be pretty rough. And if you actually look at some jet engines sort of hanging on the wing, sometimes you could actually see a droop at an angle. I'll try to exaggerate it. So here's the wing, and it's sort of hanging at an angle. Why? Because an aircraft ultimately flies at some angle of attack, and so that's actually designed to be very uniform in flight, so that you're absolutely not getting loading in that cruise condition. And then you know, a droop like that, you would take some of the loading, I guess, at sort of that takeoff condition. When you're really, I mean, at that point the air is really sucking it in. You're not so much ramming the air in through forward momentum. You're sort of sucking it in. So that's the idea behind those droops. Okay, and then when you get into that transonic regime, that kind of Mach 0.85, Mach 9, there's a lock that happen. I'll leave this picture up here. There's a lock that happen actually kind of coming around this, where you can start developing shocks. And so there's actually quite a bit of the design on most of these, what I'll call high-speed subsonic aircraft. Every aircraft you're boarding these days, commercially, that's going to fly at Mach 0.85. That is fast. If you don't think it's fast, flying 500 miles an hour, you really need to go take a flight lesson in a Cessna 172 and, you know, putz around at 100 miles an hour and understand really how amazing these machines are, that we just casually hop on and go 500 miles an hour. So you can get quite a lot of drag divergence. This is where it's going supersonic locally, and it doesn't increase drag. So a lot of design happens around that. Okay, and then for some jet engines that are designed to go supersonic, I'll sort of draw standard sort of straight jet engine like the F-16 mouth. We talked a little bit about this before, but it's actually designed to sort of have that normal shock form. And so you're getting compression that way as you're going supersonic, and you know the engine itself is sort of sitting way back here, and that's your engine. Now, a lot of times from like an F-16, it's not that close to the inlet. In ways, they kind of tuck the engine up behind. They sort of route the air sort of on this air inlet, and then back towards the engine, not the back. But you do get some compression there, and really, the diagram to take a look at, it's in the book as well. This is sort of the efficiency of the compression versus Mach number. And there is a mil spec. Did I write down the? I didn't. There's a mil spec here. I forget the actual number. And it was really just sort of this quadratic. So just a warning, that quadratic is not to be used as a this is good, this is bad. It really, you have to go back to how quickly we can calculate shock profiles now. Like I do it in Python in less than a second for me to click it. But you go in the BAST, right, these calculations, isentropic calculations, were not fast. So really, step one, you have to imagine this is a quadratic, so you can hand it off to an engineer separately who's designing the engine and sort of understand what the pressure recovery is. But for some designs, you can have worse, and some designs you can have better. So this is not a, you know, this top one being sort of your perfect recovery. So don't get too hung up on this mil spec other than understanding some can be below and some can be above. It really depends quite a bit on the design. And so to sort of draw out here in a little bit more detail, when we're talking supersonic inlet designs, okay, I'll try and draw this really carefully. Okay, something like this. We'll start there, and then I'll draw sort of the top one here, okay, with a gap. You'll see why here in a second. All right. So what this is, what I'm drawing here, and maybe I'll go a different color. So this is sort of center line, if you will. This could be a SR-71 like revolved spike, or this could be just a flat spike. So what's happening? This is the leading edge, and these angles I've exaggerated. So don't get an idea of what these angles are really supposed to be. So at some speed, you're going to have a shock wave, and if you're not the faster you go, the more the shock wave is going to get closer to the lip. So here, let me do this in orange. It really jumps out. Okay, so there's shock wave, and there's this could be Mach optimal, and this is Mach less than optimal. Okay, that's a less than sign. So when you're running not quite at your optimal condition, you're going to have air that spills over and isn't coming into the engine. And that's okay, you account for it. That's part of the sort of the spill drag. And then your optimal one, what's going to happen there, you actually want it to barely miss this front lip. And then the front lip is going to create another shock. And so this first hole, the point of this first hole is you actually are going to design this to have a bleed so you can take some air out of this. Why? Because there's a boundary layer. I'll put it in red. Hopefully that comes up well enough. There's a boundary layer here that's growing. And if you don't suck it down, then this shock, you really want the shock to hit metal and be a very clean reflection. Okay, so that you get a reflection. And really the same sort of thing, this hole, all right, not to scale. I'll move this hole back a little bit. Oh, color dance. There we go. You want this reflection to be clean and give you another compression. So you would get compression number 1. So this would be shock 1, shock 2, shock 3. So this system is going to give you 3 clean shocks because you are sucking the boundary layer out of the bottom one, and the growing boundary layer here gets sucked out this hole. So 1, 2, 3, and then a 4th, right? And then you can talk about even another one. So you can get a decent shock train. So that's how you start getting some of this performance that's above the mill standard, is if you can get multiple clean shocks in your inlet. Okay. So there's a lot there. Even that just super basic design of sort of mixed compression supersonic systems. It's what we're having to do here at Venus to power up the detonation ramjet, and it's yeah, it gets quite complicated. And this whole shock train, so the word unstart I mentioned earlier, this whole shock train is where there's been some imbalance in pressures and adverse pressure gradients. We've talked about in other courses that how your boundary layer grows, it actually can spit out this entire shock train. And all of a sudden, thunk, this is out. The airflow is now going around this. Your engine has lost all of its compression, it's lost all of its thrust. If it's a ramjet, it's flamed out. And you have now an engine that's off. And so, as I mentioned, the SR-71 pilots will have to yaw, but sort of get back down to a speed and altitude where they can relight, restart. And of course, at the SR-71, it started with the slugs of TTEB. And they would only have a very limited amount of starts they could start that engine with before it was, before they were flying somewhere with one engine at limited range. Okay, and the nozzles, pretty simply, nozzles are fairly basic things. And so at the end of your engine, if you just have a converging section, because this is sort of hot and high pressure, so I'll say this high pressure, you want to accelerate this down and create a supersonic jet. And that's to convert as much of that thermal energy, even this jet energy, even without afterburners, to convert that into thrust. So I say it's sonic, you want to increase it. If you're subsonic, you want to match it. If you're supersonic, you might as well go sonic and try to match as much as possible. And that's very simple. It's very simple to make a mechanism that only kind of closes. And you see some of those, right? On almost all the fighter jets have movable nozzles to sort of, they have to be in different positions to light the afterburner and get different thrust profiles. So that's pretty neat. And there are some that are these, I think the F-15 has a converging, diverging nozzle that can also swing open. So a regular rocket would just fix this, but the converging, diverging, so this is converging nozzle, and this is a converging, diverging nozzle, or CD nozzle. And what that's going to do is accelerate the exhaust flow to supersonic here, and then this exhaust flow will be greater than Mach 1. And so if you're supersonic, you can match that. And again, there's what you want to do from that jet efficiency point of view. Whatever your speed, your air is coming in, you want to take a lot of air and only increase the speed a little bit. That's how you get good thrust. Okay, and so that's what happened with kind of an afterburner setup, converging, diverging nozzles, and we'll have to use that here at Venus as well. All right, so a couple other fun things. I'm going to show you a picture of thrust reversers here in a second, so we'll talk about that. Thrust vectoring, you're starting to see that on some advanced fighters, and that's where you can take this exhaust and some pretty cool sort of elbows, if you will, kind of rotate, and effectively the thrust vector can change like this. I think the F-22 literally deflects it, And so, anyways, there's a pretty cool things, and that really enables, especially fighter jets. You can't imagine a world where you do this in commercial aviation, but it enables fighter jets to really have some incredible maneuverability. Okay, and then the other part here coming out of an exhaust, you'll see this very much so on subsonic, is actually so I'm drawing a subsonic jet engine here, and here's your fan. Okay. And the core of the engine may continue like this, but even coming out of this fan, what you would see is chevrons. So you would actually, kind of the ring here, it's got a whole bunch of chevrons, and they've actually shown that reduces the sound. So the sound is coming from shear layer, and it's kind of Kelvin-Helmholtz vorticity. So if you generically have, so a layer velocity here, where layer 1 is much faster than layer 2, what you're going to get, right, you're going to get these sort of vortices that generate off of that shear layer. Okay, they kind of roll up. You see beautiful pictures of this, like clouds. But this is going to radiate sound, and it's absolutely related to the frequencies and then the power here in that shear layer. And so having the chevrons literally kind of disrupts this and just makes these larger scales go to smaller scales, which dissipates it quicker. I have some discussion of this in when I talk about turbulence, kind of the last book club. So that's the sort of noise abatement on the nozzle side. And again, lots of work there as airport noise regulations are getting stricter and stricter. Okay, so I'll finish with thrust reversing, and this is really cool. You can see this engine with this outer cowl off, but the thrust reversers are literally these clamshells that when you land, these clamshells pop out, and this is sort of showed it in the almost completely deployed position, but these literally come down and close, and so the jet exhaust hits this thing and now actually bends back at, like, if this is 90 degrees, it's like 120 degrees, kind of top and bottom, and so literally you'll hear a plane land, and then you'll hear the jet engine spool up, and then like full on, full thrust, and it really helps them land in a good clean distance. So very important technology. It's actually pretty slick. It seems pretty slick and very reliable. This is a very simple system. It's just a hinge kind of coming down, and you get the ability to really do some assisted braking. So that's Inlets and Nozzles, and really that's this book club in a wrap. So again, this is a phenomenal book. Go dig in and do some of the homework problems, and especially the design example that really arcs throughout this. Even if that's all you do and go read all of those blue pages with all of this sort of design example all the way through. It's really phenomenal. I'm so glad they wrote that book in that manner. It really just helps you highlight all of these sort of concepts that I'm sort of doing the high level concepts, but you really get an idea how the deeper level calculations and trade spaces really happens kind of throughout that existing example. So go read, and we'll see you next time on Book Club.